Okay, so this will conclude the first day of the lesson, in which we will talk and discuss about Le Chatelier way to express it in graphs. So what we saw on the first part was Le Chatelier on the words. So what is happening when the concentration and when the temperature and all that pressure and volume is changing. And now we will see how can we represent that into graphs. Okay, so again, this will not, hopefully will not be too long a lesson, because what we did on the first one, it kind of made sense. I will just pause the video for a second and then have a graph and then explain it to you in a very clean way. Okay, so here's what we have as a reaction. N2O4, which is an endothermic reaction, is producing, or is reaching the equilibrium to 2 and nitrogen dioxide. So in 1 minute is reaching the, or it's reaching the equilibrium, and 1 minute from the reaching the equilibrium, what is happening is that the temperature is, let's say, decreased. Now, what did we say when the temperature decreases? So when the temperature decreases, the heat here is taken out, which means that what will happen with the reaction will shift to the left, okay, to produce more heat based on the Le Chatelier's principle. The system will react to cancel to wear off what was introduced. So if it is shifted to the left, what it means that N2O4, which is on the reactant side, on the side that the system is shifted, is increased in the concentration. So that increase will look something like this. And then it says on the book that it is reaching the equilibrium at 3 minutes, not seconds. Okay, so we'll come and we'll reach something in here. So the change in concentration for N2O4 is something like this much here. Let's take a look now what is happening with the nitrogen dioxide. So now if the system is shifted left, more N2O4 is produced, which means that the concentration of NO2 is decreased. But how much is it decreased? So the concentration of NO2 will be decreased and will reach the equilibrium at 3 minutes. And how much is it? This is parallel lines. And how much is it? Is at the same ratio that the coefficients are at. So if this is 2, this is 1. So if this is 1, then this will be 1 and 1. Okay. So now let's take this and analyze what this part of this graph means. Okay, so the first part here, this part here, where the system is to have a certain concentration, the system is in equilibrium. Okay, and then right at 1 minute, what is happening is that a stress is introduced to the system. The stress is introduced. And the stress that is happening in this particular situation is that the temperature is decreased, which means that the system will shift to the left. Okay. If the system shifts to the left from 1 minute to 3 minutes, it's the disturbance of the equilibrium system is happening. So they're trying to reach a new equilibrium. So from this area here, what is happening is that all of this shift is happening. What is going on? What is the concentration? So stress is introduced, temperature is decreased, shift to the left is happening, and it's happening gradually. Okay, the concentration of NO2 is decreased, okay, and the concentration of N2O4 is increased, okay, and on this area here, the new equilibrium is reached. And as you see here, the new concentration of NO3, NO2 new concentration of NO2 is introduced, and this is lower than the original concentration, and a new concentration of N2O4, which now is reached, which is now higher than the original concentration of N2O4. And now if we tie now this that we said here with what we said at the very end of the previous video, then we can see that the new equilibrium constant is established now, the system is having a new equilibrium constant, okay? Because heat is the only one that not only changes the way that the system is shifted, where is it shifted and how is the concentration changing, but it is given even a new equilibrium constant, okay? Let's do this now, the same example with the temperature increasing. So now let's see the same example with the increase of the temperature. If the temperature is increased, then the heat will be increased. So then the system will say, no, I don't want to be introduced to a new change. Therefore, I will use up, or I will try to undo what you did to me. And it's trying to undo by shifting to the right. By shifting to the right, what is happening, the concentration of NO2 will be increased. Therefore, the concentration of N2O4 will be decreased. Let's introduce this now, or let's see what is happening here. So we said that the heat is introduced, and in 2-3 minutes from the moment that we are observing it, what we will see is that the equilibrium is reached again. So now, if the concentration of NO2, this is NO2 here, and N2O4. If the concentration of NO2 is increased, then will be increased gradually, okay? It will be something like this. And here is where at 3 minutes, the equilibrium is reached. And now, let's see, we say that the concentration of N2O4 will be decreased, but how much will it be decreased? If this is based on the ratio here, 1 and 2, if this is increased by this much, which is representing 2, then N2O4 will decrease half of it, or because the ratio is 1 to 2. So will be something in here. Okay. Yeah, will be gradually decreased here. Okay, therefore, again, we'll reach the equilibrium and then will stay constant. So this one is 1 unit because this one here is 2 units. Make sense? Makes sense. Therefore, new equilibrium is reached, which means that new equilibrium constant because heat is or temperature is affecting the change, is stressing. And again, here is where the stress is happening, is introduced. Here is where the equilibrium is reached. New equilibrium is reached. Here is, again, equilibrium. And new concentration of NO2 is increased. It's higher than the initial concentration, and N2O4 concentration is decreased, and Kc is changed. Now let's graph change a stress in concentration. So what is happening? We have a reaction in which what you are doing is you are changing the concentration. When you change the concentration, the change on the concentration usually happens immediately. So the graph will look something like, I will draw the graph and then explain it to you. So let's suppose that we have this situation. So we have a compound and then we see a spike, and we are talking now that the stress in concentration. So when the concentration is happening, you are dumping something into the compound, into the beaker, let's say. So you are adding more of the solution of the compound into the solution. And then what is happening is that the spike is happening like this immediately at that, let's stick with 1 minute and 3 minutes. So, and then as a result of this, a new concentration is reached. However, during this time, so this is the stress. This is the old equilibrium. This is where the shift is happening. So as a result of this, this is happening. And this is new concentration equilibrium is reached. Which is always higher than the original. So never as low as the original. So you have to draw this dotted line here to show, to indicate that the new concentration is never as low as the original concentration that you had here. And when the concentration is decreased, so this is expressing stress in concentration increased. And on this case, what is happening is here is the equilibrium, and here is the stress, which in this case is the concentration is decreased. Here is where the shift is happening. And this is the new concentration equilibrium, which is never as high as the original concentration. So again, you see those dotted line here, which represent the old concentration, and the new concentration is never as high as the original concentration. So we are dealing again with the same equation so that it's easier and you understand the basic of it. N2O4 and heat is producing 2 moles of N2O2 and NO2, sorry. And the stress that we are doing is that we are increasing the concentration of NO2. By increasing the concentration of NO2, the system will say, I don't like this. I will try to undo what you are doing. And is undoing it by shifting to the left. By shifting to the left, what you are doing is you are increasing the concentration of NO2. It's produced more N2O4, so therefore the concentration of N2O4 is increased, and it is increased at the ratio 1 to 2. Okay, because this is what the balanced equation is. So the increase on concentration of NO2 is immediate and will be this much. Okay, now 3 minutes is reaching the equilibrium, but as we said, it is never going to be the same as it was the original one. So now the graph will be something like this. Okay, so this is how much the concentration is increased, which means that the N2O4 will increase the concentration by half of it, because if this is 2 parts, then we'll increase the concentration by half of it. So we'll come to a point, it goes like this. Okay, and at 3 minutes, it is reaching the equilibrium. Actually, I have to do this by better. Okay. The same thing is happening if you decrease the concentration of NO2. So we'll go down and then we'll reach certain equilibrium, and then that and that. Okay. Now let's see a case again for the same equation, because I'm trying to make you understand the concepts that stand behind it, and we will do more examples like this either in a separate video or in class. So the change or the stress that we are implementing to the system in equilibrium is now the change in volume. Think about it, volume and pressure are the inverse of each other. So even if it is increase in volume, then you will see a decrease in pressure, or if it is a decrease in volume, then you will see an increase in pressure. I probably write it here. So if the volume is decreased, then pressure is increased. Or if the volume is increased, pressure is decreased. So this will be the same thing if we are saying here in this case, when we are saying that the volume is increased. And how do we see that? We see a spike, and both of them are increased immediately. So that it's not that one is, the stress is that they are both increased immediately. So now, based on the Chateliers principle, then a shift will happen. Okay. So now, uh, just to clarify here, that this line that you see here is the stress that is implemented, and this is how you realize what is happening here. Okay. The stress that is implemented, and the increase is the same. It's not based on the ratio at that moment, because let's suppose that you have a container and you are pushing the piston up or down, then the volume of the two will, the stress, the immediate one, will happen will change at the same time. Okay, if you have a container 10 volume and you are going from 10 volume to 15 volume later, then both of them will have a freedom, quote unquote, of the 15 volume. And now see what is happening here. Okay, what we are doing is we are changing the volume, and then we said that in order to counteract, to react the pressure pressure, then the volume is decreased. Okay, so we are saying here that the volume is decreased. If the volume is decreased, then pressure is increased. If the volume is decreased, sorry, the volume is decreased, pressure is increased. Okay, if the pressure is increased, then the concentration of both of them will be increased. This is why you see on this case is increased as well, because volume is decreased, meaning that from 10 liters it's going now to 2 liters. Then those the concentration, moles per volume, moles per liter, is increased. This is why you see this spike here, and the spike is the same for both the reactants and the products. Okay, so now in order to react the impulse in the pressure increase, the equilibrium will shift to the side that has less moles of gas. And where are less moles of gas? Into N2O4. Okay, so will shift to the left. Okay, will shift to the left. Therefore, the concentrate will have more N2O4 will be produced. So we will see an increase like this. And now this increase is 1, let's say. And then where is it coming from? This increase is coming from decreasing the NO2. Will be, let me draw it again, will be something like this. Okay, 2. Because the ratio is 1 to 2. Okay, we'll see one example where the coefficients are the same, and then we are done with this video, with this part of the video. And as I said, we will see more questions like this in class. If we have a reaction in which the ratios are the same, then let's say something like this, NO2 plus gas, of course, plus carbon monoxide, carbon dioxide, and nitrogen monoxide. So what do we see here is all the ratios are 1, 1, 1, which means that even if a shift or a stretch is happening, then still will be the same thing. Nothing, the shift will not happen. So if you have here the NO2, concentration of NO2, and then you move to concentration of CO, and then you move to concentration of CO2, and lastly is the concentration of NO. So if a change is happening, let's say an increase is happening, then they all will increase at the ratio, whatever the increase is happening, but then will be the same. So no time to reach the equilibrium. It's like will be this. Okay. And last, this one here. So all will be the same, even at 2 minutes and 1 minute and 3 minutes. So will be the same. Nothing will change. And the same thing is happening if we add catalysts. Still will be the same thing. Will be the same thing. Nothing will change. We'll have, let's suppose, NO2 and concentration of NO2 and N2O4, the same thing that we had. And here in 1 minute, we add a catalyst. Nothing will change, still will be the same thing. They will go faster, but the same, both forward and reverse reactions will happen faster, but nothing will change. The Le Chatelier graph will look the same even after you add the catalysts. As I said, those are pretty much the basic of the graphing, Le Chatelier's principle. We will see more in class like this. So watch the videos and be ready to see more examples in class. And if I feel that the students need to have this in a video, then I will make a new video for that with more examples on it. See you in class.